So welcome back, everybody. It's good to see you all. Your mics are muted during this part of the session, although I can unmute them at the end. So to ask questions or make a comment, just type in the chat window. This has been a rough couple of weeks for all of us, and I think it'll help to get back to normal and make classes as normal as possible. We all have adjustments to make here with learning to use Zoom and online modalities for classes. You're probably at this point more expert than I am, but we'll all learn together. I know it's going to be a learning curve for me, and as we go along, I'd appreciate suggestions about how to make this work better. My plan is to try this for a couple of weeks and see how it goes, and then see what adjustments we have to make. These lecture sections are being recorded, and I will post them in Canvas so that you can review them, or people who can't make it can actually see the recording. The recording will be the video only, not the chat. There is a Zoom phone app, so in principle you can join from your phone, although I think a bigger screen is easier, but whatever works for you works. At this point, reading the book is probably one of the most important things you can do. We're not going to be able to cover everything in lecture. We never have been able to cover everything in lecture, but the lack of the diminished contact means that the book is an important resource. I'd suggest skimming a chapter before lecture just to see what to expect, and then reading it carefully after lecture to really solidify knowledge and identify any questions you've got. I know that you're coping with a lot of disruptions in your lives, and some people have already let me know that they can't attend lectures regularly. I get that, but I do think there's some value in staying as connected as we can. So I hope this will actually work for us. If you can't come to class, there is another way to engage with the class and get some class participation, which is I've created a discussion board, a discussion in Canvas. And you should use that to post questions, answer other people's questions. It's not the way we've been working together, but we can certainly try that. Just so I have a record of who's here today, I'd appreciate it if you just type your name in the chat window. The chat will be stored separately when the recording's finished, and I'll just have a record of how many people made it, so I'll know how well this is working. Thank you. And you ought to have everybody ought to have their mic muted. If you have a request, please type it in chat. So we have a lot of logistics to talk about before we get started. The first thing that's probably on all of your minds is test 2, which was supposed to be last week. We will have the test this Thursday during the regular class time. It'll be in Canvas. It'll be timed, so you'll have 80 minutes to do the test unless you typically get extra time, and then you'll get extra time on the test. Because it's in Canvas and it's the first test I've done in Canvas, it'll be almost entirely either multiple choice or what I call multiple select. Canvas calls multiple answered, which means check all that are true from a list of possible alternatives, so sort of multiple true false. I'll probably throw in one problem that asks you to calculate a numerical value just to experiment with that and see how well that works. Because that's obviously another modality for future tests. To keep it simple for this test, I'm not going to do show your work questions. So almost all the problems on the test will be either one-step things or maybe to be a little harder, at most two steps, but they won't be the complicated show all your work problems that we've had on other tests. We'll experiment with that in the future, maybe depending on how this goes. Because I'd like you to be able to use GlowScript for your calculations, I will not require that you use the lockdown browser. You'll be able to use Chrome or whatever your favorite browser is. And I'll just rely on your integrity. I don't think you're going to cheat. Please don't cheat. I know it's a little more tempting when you're off by yourself, but I have confidence that you won't. The rules are the same as for previous paper tests. You can use as blank paper, a pencil, a calculator, or GlowScript, or Trinket, or Maple, or Mathematica, or whatever your favorite calculation tool is, but not refer to previous work or other people, real or virtual. I don't expect problems. If you do spectacularly better than you've done in the past due to studying for 2 weeks over our extended break, then I'll rejoice, and I might ask you to explain your work to me privately, but I don't expect any problems. There will not be a recitation Thursday after the test, and we'll start new material next week. So does anyone have questions about, can I make the test available all day on test days? I am, okay, so I'm not excited about doing that, but it's a possibility. If you have constraints where you can't, where you think you're not going to be able to work the test during the normal time, could you please email me and let me know that? I'll consider making the test available all day on test days. How is recitation going to work? Will there be a worksheet posted on Canvas? Yes. I'll post practice problems, and then I'd like to try breakout groups on Canvas, on Zoom, letting you work together on these things, and experiment with that. For today, for recitation, what I expect to do is work on problems from the practice test or other problems that you suggest that you'd like to review. The practice test is posted on Canvas. As I said on the test, it's not really quite like the test you'll have in Canvas because it's got a lot of longer problems on it, but it's similar in substance. Other questions about tests or recitation? Is the material covered the same as it would have been last week? Yes. So it's chapters 16 through 19. Excluding today's lecture, I'm going to just do a brief, what today is going to be mostly review. I don't think it makes sense to start something new today. So I'm going to talk about one or two things at the end of chapter 19 that we didn't talk about before that will not be on the test, and then we'll review some important ideas from chapters 16 through 19. Homework. Note that there is a homework assignment due today, the chapter 19 homework. Now, I'm sure you've all finished it long ago, but if you happen to have forgotten about it, it is there, and it's important to do it because this is material covered on the test. Where do we turn in the makeup quiz today? What you're going to need to do with the makeup quiz is take a picture of it or scan it and email it to me. You probably could take a good enough photo with your phone that I can read it. Office hours. Both James and I do plan to do office hours on Zoom. I will probably send you a Qualtrics poll just to see when that would work. Both of us plan to have some evening office hours. For today, you should assume that office hours are the same as the regularly scheduled office hours, and they will be on Zoom. And I need to post the link at Canvas, don't I? Try to remember to do that. Let me write myself a note. Okay. So any other sort of logistical issues that you'd like to raise? Okay. So I would like to go back to the end of chapter 19 and talk a little bit about batteries and meters and capacitors. And what I'm going to do here is I'm going to share my screen, which means that you'll no longer see a professor with glowing purple eyes, which is a reflection from my screen, but which it's whatever makeup, whatever the last makeup quiz was it 17 or was it, no, it was 18. So what I want to talk about here is real batteries. This is section 19.5 in the textbook. And what's the difference between a real battery and an ideal battery? Well, charges moving through a battery have finite mobility. They can't move infinitely fast. And some of the work done by the battery ends up heating the battery. So we model this as if the battery, a battery was just a power source with our standard battery symbol here, in series with a resistor, which we call an internal resistance. So that a circuit that had a battery and a light bulb, we would actually model as the battery with an internal resistance, and then the resistance of the light bulb. So this combination is called the real battery here. So what does that mean? That means that a loop equation for this circuit would look like this. So a delta V round trip would equal the EMF of the battery minus the internal resistance times the current minus whatever this resistor is times the current equals 0. So this is the potential difference across the battery. This is the potential difference across the internal resistance. And this is potential difference across the resistor. A fresh D cell, like the ones you've been using in lab, has an internal resistance of something on the order of about 1/4 of an ohm. So let's think about what would happen if we connect different resistors to the battery in a circuit like this one that we've drawn up here. So consider different resistors. So we'll say this is the resistance. This is the current if the battery is a real battery. And this is the current for a real battery. So let's say we have a 100 ohm resistor hooked up to, we'll say the battery, the EMF is 1.5 volts, just like your D cell. So for a 100 ohm resistor, if we didn't consider the internal resistance, then we just have I is 1.5 volts over 100 ohms, or 0.015 amps. In the real battery case, we have the current is 1.5 volts, the EMF of the battery, divided by 100.25 ohms, which isn't really very different. It's about 0.01496 amps, so not much change. If we have, now for an ideal battery though, if we make the resistance smaller and smaller, the current just keeps getting bigger and bigger. So if we have a 10 ohm resistance, we get a current of 0.15 amps. If we have a 1 ohm resistor, we get a current of 1.5 amps. And if we add, we don't have any resistance at all, so we add 0 ohms here, the current would be 1.5 volts over 0, which would be infinite, which is probably not what we're really getting. So let's see why not. Here we have, if we have a 10 ohm resistor, now the current would be 1.5 volts over 110 ohms, 10.25 ohms, that's what I really mean, okay, which is just the sum of the resistances of the total resistance here. And so what we're going to get is about 0.146 amps, still not very different. When we get down to 1 ohm, though, we find that we have 1.5 volts over 1.25 ohms. And now we're getting only 1.2 amps instead of 1.5 amps. And in the case where we have 0 ohms, I would be 1.5 volts divided by, well, we still have this internal resistance, 0.25 ohms. So we'd only get 6 amps, which indeed is about the short circuit current from your battery. Now let's see here. Is there a way I can actually see the chat while I'm sharing a screen? Okay, I don't think I can actually see the chat. I'll have to experiment with that. So what I'm going to do is stop sharing my screen for a minute and see if you have questions. Okay, so what question is, what does short circuit actually mean in this sense? And what a short circuit really means is that you've added something close to zero resistance to your circuit. So in your case, you could make a short circuit with one of your batteries simply by taking that long red wire in your electricity kit and connecting that directly to the battery. And you did that actually when you were measuring the magnetic field of a current in a long straight wire. So you made a short circuit. The idea is that that wire doesn't have zero resistance, but it has very low resistance, and it's probably low compared to the internal resistance of the battery. So the total resistance of the circuit was really dominated by the internal resistance of the battery. And so instead of getting an infinite current, you got a 6 amp current. Now, you might not have gotten a 6 amp current if your batteries were old, because the internal resistance of the batteries increases as they age and they use up these molecules that are reacting to release electrons and take them up on the other end. And so so you might have had less than a 6 amp current in your short circuit you made with the long straight wire in lab. Other questions about that? Okay. I'm going to go back to sharing my screen for a minute, just to talk very briefly about ammeters and voltmeters. Now, you've used a voltmeter in lab. So and you've used a voltmeter to measure potential differences in lab. And so you built some circuits that involved light bulbs early on. And you used a voltmeter to measure potential differences across the light bulbs. And what you did was, to measure this, here's your voltmeter. You'd connect the leads of your voltmeter on either side of the light bulb, and you'd get some reading here of 0.75 volts or something like that. So you'd measure the potential difference between one end of the light bulb and the other. So notice that when you did this, you were building a parallel circuit. And what we saw with parallel circuits is that if we have a situation where we've got, so here's our light bulb, but if we had another resistor in parallel with the light bulb, it was the combination of both resistors. So this is the bulb, and now this is the voltmeter. The combination of resistors in parallel changed the current through the circuit a lot. In fact, it could increase the current through the circuit a lot, especially if one of these things had fairly low resistance. Well, we don't want the voltmeter to change the circuit. So how do we keep the voltmeter from changing the circuit? Well, the way not to change the circuit is very much is to give the voltmeter very high resistance. So a voltmeter, your light bulbs had resistances on the order of 10 to 40 ohms. A voltmeter has resistance of on the order of 1 million ohms, a mega ohm or something like that, or more. In order to not really change very much, as little as possible, the current running through the circuit when you're measuring a potential difference. Now, I don't think that you actually got to use an ammeter, but and the same meter you used as a voltmeter can work as an ammeter. All you have to do is just switch the dial, and switch the leads. And when you use an ammeter to measure current, though, what you do, so suppose you wanted to measure the current in this circuit, what you do is you actually have to put the ammeter in series in the circuit. So you break the connection and you attach one lead of the ammeter here and one lead here, and the current actually flows through the ammeter. So this is a voltmeter in parallel. This is an ammeter in series. And now we've made a new series circuit. Because the ammeter is a resistor. So what is the characteristic we want for an ammeter so that it doesn't change the circuit very much? So what we've got here now, if we draw it out, here's our light bulb, here's our ammeter, here's our another light bulb. So in order not to change this circuit very much, we want this to have very low resistance, so it's as close to a wire between these two other resistors as possible. So an ammeter has very, very, very low resistance. I don't remember exactly. I think it's on the order of milliohms, or maybe microohms. So when we're making measurements, on circuits, we actually are. Okay, so do you agree that was a series circuit? Okay. So does a greater resistance due to a battery or wire mean that more energy is lost for heating up that part of the circuit? Well, of course, when you have you increase the resistance, you totally change the current. So the total power output of the battery may or may not be different, but the key issue that you ask about is right, that when something has a lot of resistance, it gets hotter. And so a lot of the energy output of the battery is used to heat that part of the circuit that has high resistance. Okay. Questions about that? All right, I'd like to show you briefly an analytical treatment of what happens when you put a capacitor in a circuit. You've experimented with capacitors, and you've seen that when you connect a capacitor, an uncharged capacitor, to a battery and a light bulb, the light bulb is initially bright and then gets dimmer and dimmer and finally goes out. And in fact, you did a lab on that and wrote a lab report on it. Let's see what we can understand quantitatively about this. So let's go back to screen sharing here. And we're going to talk about capacitors and circuits with the tools that we've developed for chapter 19. So let's consider a simple circuit that's got a battery and a resistor and a capacitor. And this is the circuit you built in lab, because this is the light bulb and that's the capacitor. So that's the circuit you were experimenting with in lab. And at any time, so this is a circuit, and so we can write a loop equation for this capacitor circuit. This is called, by the way, an RC circuit. Where R means resistor and C means capacitor. And you'll see that these circuits can actually be useful in timing things, and we'll figure out why. So at any time, doesn't matter whether the circuit is charging or discharging or whatever, we still know that the round trip potential difference has to be 0. So we can write a loop equation for this circuit. We have delta V round trip will go that way around the loop. So it's the EMF of the battery minus the potential difference across the resistor, which we found was the current times the resistance. This is delta V resistor. So that's minus IR. And then we have the potential difference across the capacitor. And remember that we defined, back in the day, we defined capacitance in terms of charge and potential difference. So capacitance the amount of charge on the plate of a capacitor at equilibrium at any time was equal to the capacitance times the potential difference across it. And remember that capacitors are labeled. Your capacitor was a 1 farad capacitor. So we can write the potential difference across the capacitor in this equation here as just the charge on the positive plate divided by the capacitance of the capacitor, and that should equal 0. And that should be true at any time. So let's consider two special times. One is the final state, where it's at equilibrium. The capacitor is completely charged. We're just going to rewrite this equation. We have the EMF of the battery minus the current in the circuit times the resistance of the light bulb, but the current in the circuit is now 0. So the potential difference across the resistor is 0. And we have Q over C equals 0. So the amount of charge on the positive plate of the capacitor is just equal to the EMF of the battery divided by the capacitance of the capacitor. Another special time is the initial time. Just the instant after connection. So we have the EMF of the battery minus the potential difference across the resistor. There is a current flowing, so that's not, so this potential difference across the resistor minus IR is not 0. Minus Q over C equals 0, but initially Q is actually 0. So we get here that the initial current is just equal to the EMF of the battery over the resistance, and that's the same as if the capacitor weren't there. Now, at some in-between time, when the capacitor is not yet fully discharged, but in the process of, not fully charged, but in the process of charging, some arbitrary time, we have both terms are non-zero, and so we can get that the current is equal to the EMF minus this term Q over C, the potential difference across the resistor, divided by the resistance of the light bulb. Now, the rate at which charge accumulates on the positive plate of the capacitor is dq dt. But that has units of coulombs per second. And in fact, that's just the current, because if 0.1 coulombs per second are flowing through the circuit, 0.1 coulombs per second are flowing onto the positive plate of the capacitor. And so the current is the rate of change of the charge on the plate of one plates of the capacitor. So we can write this equation now. So if I is dq dt, and that's equal to EMF minus Q over C over R. Then we can rearrange this and we get dq, the amount of charge flowing onto the capacitor in a time dt, is equal to the EMF minus Q over C over R times dt. So well, that's, and now we can do a numerical integration the way we've been looking at motion or in the context of forces. So we could say in one step, Q is the previous Q plus delta Q. And we could actually write a program to model this. So let's see how that works out. So I think I have to stop. So wouldn't what be EMF times C? So in the initial state, the final state, oh, did I make an algebra mistake? Yep. Thank you. Yep, thanks. Okay, other things? Yeah, okay, I just corrected it. You'll see that in a second. Okay, now this equation looks like one that we could just write a program to solve. And so, of course, we turn to GlowScript for this. And so here is here's a GlowScript program. Let's make it a little bit larger, maybe. So what's it doing? Well, this is just setting up some graphs. We've described this circuit as a 40 ohm resistor. That's the resistance of the long light bulb, I think. Here, the capacitance, well, let's make it 1 farad, 3 volts, and we're going to let it run for 240 seconds. Now, what is the program doing? Well, we just took this equation, we just wrote dq, the amount of charge. We start out with q equals 0 and time equals 0 here. The amount of charge flowing onto the capacitor in a time dt just comes from EMF minus Q over C times dt, the whole thing divided by R. And then we're just going to add that to the charge on the capacitor and graph it. And when we run the program, we see that the charge builds up and eventually levels out to 3 coulombs, which is the EMF of the battery divided by 1 farad, times 1 farad. Now, what would this imply for the current? Well, the current is, of course, dq dt, so it would just be dq, the amount of charge that went onto the capacitor, divided by delta t. And so if we plot the current in another curve, and I think I'm going to have to make this a little smaller to get both graphs on, we see that charge versus time rises and levels off, and the current drops eventually to zero over time. So we're able to model, to use this equation to make a prediction of what we should see. And in fact, that does look like what we saw in those lab experiments. That we didn't see the charge on the capacitor, but what we did see is the brightness of the bulb drop and get very, very, very dim and then finally go out. So that definitely is what current versus time looked like in our experiments. And of course, the higher the capacitance, the longer this should take. So if we make the capacitance, well, let's see. If we make the capacitance 4 farads, we're not quite to the end in 200. Maybe we have to let it go for longer than 240 seconds here. If we make the capacitance smaller, or make the capacitance 1 farad, but we make the resistor 10 ohms, which is like the round bulb, that all happens much faster. It really takes much less time. So the time to charge or discharge depends on both the resistance of the resistor and the capacitance of the capacitor here. Okay, so we can do that numerically, but we can actually also do it analytically using calculus. So let's see what that would look like. Back to pencil and paper here. What we have here is an equation that has a derivative in it, so it's a differential equation. And our result looked like an exponential. So I versus t looked like an exponential. So one way to solve a differential equation is actually just to guess an answer. So we'll guess that the current as a function of time is equal to the initial current I0 times e to the minus some constant times time. We'll call the constant alpha. We had an equation that said I is dq dt, which was the EMF minus Q over C over R, which we can write as EMF over R minus Q over an RC. If we differentiate that, we get di dt is equal to, well, that term is constant. So what we end up is a minus 1 over RC dq dt, but that's just I. So we have a minus 1 over RC times I. And that does what an exponential is indeed a function that is its own derivative, modulo a constant. So let's plug in our guess. If I is equal to I0 times e to the minus alpha t, we'd have di dt is equal to I0, the time derivative of I0 e to the minus alpha t, which is a minus alpha I0 e to the minus alpha t. And that suggests that this alpha, this constant alpha, is in fact this 1 over r times c. So our possible solution did satisfy the differential equation. So we get an equation I is EMF over R, which is the initial current I0, times e to the minus t over RC. And this is an analytical solution for any time t. This quantity RC is called the time constant for a circuit with a resistor and a capacitor in it. And you can, so because when t equals RC, the value has fallen to 1 over e of the original, to 1 over e of the original value. So, and that's about 0.37. So it's, so every, for every time RC, we fall another 37% of the way. So let's think about your light bulb. Your light bulb was 10 ohms, that's the round bulb. The capacitance was 1 farad, so RC was 10 seconds, which means that in 10 seconds, the bulb had fallen to 37% of its original, the current had fallen to 37% of its original value. Now the brightness is proportional to the power, and so that would be, the power is the proportional to the current squared. So the brightness has fallen even more. And in fact, the bulb is very dim because remember, the bulb is not an ohmic resistor, so that it can get, when it's not very hot, it isn't getting off much light. So it's not the greatest ammeter in this situation. But 10 seconds is consistent with the time we were seeing for charging up the capacitor through the round light bulb. So this is, would this be an accurate equation for other types of circuits or just this one? Well, it's a circuit with a resistor and a capacitor. So it's our solution is for a resistor capacitor circuit. And you can see that this could be used in timing because current would go out in a time, 2 RC or whatever, you can watch the change of current. So RC circuits are used, in fact, in timing in electronics. Although now there are other ways to do it. Other questions? Okay. What time is it? I thought maybe one thing we could do would be to work a problem that from the textbook that just helped us review some of the things about circuits. So my proposal is that we look at a problem from the textbook, problem 66 in chapter 19, and talk about how we go about solving it. So here is the problem. We have here a circuit that's, let's see if I can make this all a little bit bigger. A circuit that's got 3 light bulbs, 2 in parallel, 1 in series. And right now there's a switch in it that's actually open, not closed. And we're asked, and we're given the resistances of these bulbs, they're all different. And we're asked various questions about this circuit. So I thought it might be a useful review to just go over this problem. There's kind of a lot of good stuff in it. So the first thing we're asked about with the switch open is, what is the charge on the surface of the circuit going to look like? So I'd like to ask you to think about that for just a minute. The bulbs are not lit when the switch is open because there is no current flowing, despite the fact that it's shown on the diagram as being lit. So the electric field inside each of these bulbs must be 0. So so at equilibrium, everywhere in the bulbs and the wires. Now, actually, if there isn't charge on the surface of the wire, the electric field will not be 0 because these batteries do have charges on their ends, and they make a dipole field. So we do need some charge on the wires to contribute to making the electric field 0 everywhere in the wires. And what's going to happen is we'll have a buildup of positive charge on the wire, presumably with more at this end, and a buildup of, on this end, negative charge along this wire with a little extra negative charge here, in such a way to make the electric field 0 everywhere. Now, the second question says, with the switch open, find the potential differences VB minus VC. So B is down here, B and C are the switch, and VD minus VK, which is across this parallel branch of the circuit. So B is switch open. V sub, what is it? D minus V sub K and V sub B minus V sub C. Well, VD minus VK in the circuit is going to be equal to the potential difference across the light bulb. So it's going to be equal to VF minus V sub E. Maybe we should write approximately equal to say that they're connecting wires, although in this case the field there should be 0, 2. And that's equal to the electric. And we can think about it two ways. We can think about it as equal to minus the electric field in the bulb times the length of the filament, or we can think about it equal to the current times the resistance. But in either case, this is going to be 0 because there's 0 current flowing, and the electric field in the bulb must be 0. Now, what about the potential difference across this open switch? So VB minus VC. Is that 0 or not with the switch open? Well, if we write a loop equation, so we can take a loop that goes that way. So we have plus EMF plus delta V VC plus, we'll go through the bottom bulb, delta V HG plus delta V M L 0. Since there's no current, we know that those are 0. And that means that this potential difference actually must be equal and opposite to the EMF over the batteries. So we end up with concluding that delta V B to C is equal to the minus EMF of the batteries. Now, how can that be? There's no current flowing there. Well, we did note that there is charge accumulated here on the ends of these wires. So there's charge on the end of that wire, and there is positive, negative charge on the end of this wire. And so in between the wires, so E in air is not 0. So with this open switch, it looks like a tiny capacitor in a way, and the potential difference across that switch must be numerically equal to the EMF of the batteries. So questions about that? No. Okay. So let's do one more thing with this problem before we We stop. We are asked to write loop equations and node equations, which we could use to solve for the unknown currents. So how many equations do we need? Well, in this circuit, we have a current through bulb 1, we have a current I2 through bulb 2, and we have a current I3 through bulb 3. And so that means we're going to need, we have 3 different things, so we need 3 equations, 3 unknowns, 3 equations. So the first thing we can do is choose location K as a node. And we say that the current coming into K, or if we're talking about conventional current would actually be going counterclockwise here. So we'll say the current coming into K, I2 plus I3 has to be equal to the current going out of K, which is I1. So we have I2 plus I3 equals I1. And we can write some loop equations. We already wrote one loop with the switch closed. So we're talking about current with the switch closed now, sorry. So we'd have EMF, the potential difference across bulb 3 and the potential difference across bulb 1. So we'd have EMF minus I3R3 minus I1R1, which are the equals 0. And then we can choose one more loop equation. We could actually just do a loop around this little internal loop. The only rule for a loop is it can't cross itself. So if we go that way, conventional current is going to the left here. So this one would be positive and that one would be negative. So we'd have I2 R2 plus I3 R3 equals 0. And that gives us enough equations that we can actually solve the problem and get the currents. We can do that by substitution. We'll leave that as an exercise to the reader, and I will note that this problem is actually too long to be a one-step problem on a test, although pieces of it could be broken out as steps in tests. Questions about this? Okay, well, I'm inclined to stop here, and I'm going to unmute you all so you have a chance to, can you row reduce? You can use whatever system you want for solving simultaneous equations. I like substitution, but if you want to do matrix operations or determinants or adding equations or your favorite way of solving simultaneous equations, you can do that. How do you sign attendance? Just type your name in chat. So if you haven't done that, please do it. The chat will be saved separately from the recording, which I will attempt to process and post in Canvas. Thanks for coming. I will post I'm using the notes are in OneNotes. I can actually potentially post my OneNote notes. Yeah.
That
So
would be great.
yeah, so I'll post the OneNote notes in Canvas so you can see the transcript of the whole thing. OneNote is free, I think, on Macs as well as PCs, so I don't think you should have a problem getting in it. Okay, it was great to not exactly see, but kind of see you all again.
Spirit.
Yeah, exactly.
So Dr. Chabay, just one quick question.
Yeah.
So you said that, like, today's note is just like the review of what we previously had the past couple of weeks, but
this was new material. No, this is not on the test, because remember the rule for a test. Remember the rule for a test is you have to have done homework on something, and you haven't had homework on this.
Okay. Thank you.
Recitation, you come to the same Zoom link. What you'll find is that there is a link in Canvas for the recitation, so it shows up in the Canvas calendar. It's a recurring meeting. Okay, so there's a separate Zoom link for that. And office hours. What were James's? One of us will have office hours this afternoon at the usual times on Zoom, and I will post that on Canvas. It'll either be me or James. I need to talk to James. Okay. Okay. Okay, and I will post a link to this OneNote document in Canvas also.
So come back on the chat.
No, it's not. The syllabus does not say that. It said that at first, but if you look at it now, it's all the way through chapter 19. It was changed for a while. We've gotten. It includes everything that you have homework on that's due this evening. Yeah. So the test covered all of chapter 19 except what we did today. Yeah, that was a really important piece of knowing about potential differences. So starting at C, ending at B, and that's C to B. We could also write that VB minus VC. So that's right.